Thank you, Ben. The hydrogen industry hasn't realized its full potential, partly because we've been unable to articulate and sell the concept of renewable source hydrogen as a complete energy system, solving both the transmission and the firming storage problem for the renewable energy industry. We can run the world on renewables, and we must do that with some nuclear, of course, but we can't do it with electricity transmission alone. So we need to focus on complete renewable energy systems. Here's one. The sun's gone down. The PV is no longer producing electricity to split the water molecule to make hydrogen and oxygen to go to the fuel cell to produce DC electricity to do work, which is what we humans want. So either we have a perpetual motion machine here or we have storage in the system someplace. And we'll talk about storage while you place your bets on whether this is truly perpetual motion or not. From the electric output of wind and solar plants, electrolyzers, compressors, we can pipeline that energy large distances to our city gates for utilization by a variety of people. High pressure output electrolyzers are becoming available, so we can perhaps eliminate the compressor, go straight into the pipeline at 1500 psi, suffer the friction losses, deliver at the city gate market at 500 psi to our various customers. The pipeline itself, packing and unpacking as they do in the natural gas industry, provides a very large amount of storage. And if we can access geologic storage, and the only geologic that probably is going to work is solution mine salt caverns, very large, 600 to 800,000 cubic meters of physical volume, 700 meters or more below the surface, capable of storing 2,500 metric tons net of hydrogen. That's about 92,000 megawatt hours of energy as the chemical energy in H2, at a cost of about 16 cents a kilowatt hour. That's the lowest cost energy storage known to man at this time. And in a study that we did for a private firm, you can pack these very close together geologically if they're all manifolded together and all operating at the same pressure, so there's no differential pressure trying to collapse the salt cavern walls. Compared to any known electricity storage, hydrogen and anhydrous ammonia, which looks like a very good transmission and storage medium too, are literally off the charts in any comparison, any attributes. Of course, the topology is quite different. If we have no connection to the electricity grid, everything is done via pipelines, and we're delivering only compressed hydrogen to a pipeline network for long-distance transportation. Everything is quite different. Of course, when we bring it to the city gate market, we can fuel vehicles, combine heat and power, and do other things. There's probably a better way to do this renewables hydrogen system than what we've done so far. And when these become emergencies, we are going to quickly want to invest in conservation and efficiency first, and then in gigawatt scale renewables. We have to think beyond the electricity grid because we just can't build enough electric lines and store enough energy to give us firm renewable energy, and that's why hydrogen and ammonia look particularly attractive. DARPA has been around for several decades. At the beginning of the Obama administration, they said, let's emulate that and call it ARPA-E. Their third solicitation, they've been around less than a year, third solicitation included grids. Here's their acronym. And our small company responded to that funding opportunity announcement with a 5-page concept paper. On the 23rd, they said, you're not encouraged to submit a full application, but we can do that, due 24th of May. Their goal for storage on the electricity grid is $100 per kilowatt hour capital cost. Cavern storage of hydrogen is 20 cents a kilowatt hour. So it's compelling. They should have taken a closer look at that, I think. But we can still submit a full application, and any of you who would like to can join us as co-applicants in that final application. Widespread deployment of grid-scale energy storage. If you had a ubiquitous hydrogen pipeline system supplied with renewables, as we have the natural gas system now, then the storage problem was essentially solved. Not only storage in the pipeline, but storage in the caverns. So our concept paper, which we submitted, was to assemble a collaborative. Only $600,000 now, but let's assemble a collaborative and pay their expenses to get together to begin the process of conceiving, designing, and bidding a pilot plant for renewables to hydrogen pipeline to a utilization center. And also to do the R&D and demonstration necessary for a new kind of line pipe. We probably can't use steel pipe in renewables hydrogen service because the pressure fluctuations are so great. So therefore, polymer metal line pipe looks attractive. We applied for $600,000 cash and in kind. Here's the opportunity, an extraordinary opportunity, not very promising, but maybe something would be accomplished by submitting that. I offer you 5 hypotheses. First, we can run the world supplying all of humanity's needs on renewables. It'll be a combination of distributed and centralized. Centralized is the big wind plants in North Dakota, and that's where the pipelines are particularly useful. It has to be affordable, has to be benign source, it'll be from diverse sources, synergistically combined, we hope, to minimize the transmission and storage we need. But darned if the richest resources aren't stranded, far from markets with no transmission. So we must run the world on renewables because this is capital. And when we spend that, we go out of business. So we need to draw a dotted line here. This is the annual input of renewables available to us. This is humanity's total world energy use. It's compelling that we do run the world on renewables. There's this many kilograms of annual hydrogen production available in the wind Great Plains. There's 3 orders of magnitude more from solar sources. Synergistically combined, because they are diurnally and seasonally synergistic, we can minimize the amount of firming storage that we need. Here's the wind resource, 12 states, fully harvested with about 3 million megawatts of wind plant. We produce about 10,000 terawatt hours. That's about 100 quads, the entire energy consumption of the USA. We could export it in new high voltage DC electric lines. We'd need about 900 of those, 500 billion. We could do it as gaseous hydrogen pipelines, need about 400 of those, 400 billion. Comparable capital costs, but the hydrogen pipelines are underground. And the pipelines have very large capacity. According to our hydraulic modeling, for a completely compressorless 500-mile long hydrogen pipeline system, the capacity is about 8,000 megawatts. If you suffer the friction losses, 1,500 psi in, 500 psi out. That's your city gate market. And gigawatt mile should be the unit of capacity for all transmission, whether it's electricity or pipelines, gaseous hydrogen or other. And per gigawatt mile, hydrogen pipelines are significantly less costly than electric lines, as well as being buried underground, out of sight, out of mind, and not subject to acts of God and man. Second hypothesis, when we realize these as emergencies, we'll quickly invest in efficiency and conservation, and then in these large new gigawatt scale renewable energy supplies for which we need transmission. Third hypothesis, the shortest path to this benign, secure, and abundant energy future is going to be from renewables. It's from centralized sources, and it's via gaseous hydrogen pipelines, because we can avail ourselves of geologic storage to firm that supply. But this hasn't been done, and therefore a pilot plant is needed. And we need to get started on that process now. The process of conceiving, designing, and at least bidding to find out if we can put together a credible RFP and RFQ to see if anyone will even take this idea seriously. We called it in several of our co-authored papers the International Renewable Hydrogen Transmission Demonstration Facility. How's that for an acronym? Anhydrous ammonia looks attractive too, but we do have examples in place. We have an extant transmission network for that now. Fourth hypothesis, hydrogen's principal value is not fuel for fuel cell cars, although that's a perfectly good use for it if we had it, but rather the means by which we gather, transmit, and store these large, diverse, renewable energy sources, firm the output with storage. It's going to be a benign energy system if these are made. This hydrogen is made from renewables. It's a global opportunity, not just North America. And we should talk about a hydrogen sector, not a hydrogen economy, because we need to focus on systems, complete renewable hydrogen systems of production, transmission, and firming storage and utilization. Fifth hypothesis, this is a major new industrial process for which pilot plants are needed. Every major new, this is the acronym that we gave it, and it's featured in several papers that we've co-authored with Japan and Canada, where we focus on renewable hydrogen systems. Here is a graphic we presented at the World Energy Congress in '04. I have some handouts up here, including this graphic. It's a little hard to see here. The trouble with renewables, of course, is that they're diffuse. They're dispersed all over the countryside, so gathering is needed, transmission is needed, the richest resources, the high intensity and large geographic extent, and the time-varying output or intermittent nature of them. Here's a week of wind performance. Here's a different week of wind performance. Look at the different challenge that this places on the utility system to compensate with coal and other generation for the different availability of wind over a 1 week period. This is wearing out their combustion turbines running on natural gas, trying to follow this kind of output from the wind machines, and nobody's paying them for it. Seasonality of the Great Plains wind is a big problem because it's 20% windier than normalized in the wintertime, and the spring is 30% less windy in the summer. So somehow that has to be stored. There's the ditch that you have to jump if you're going to deliver the same amount of firm energy every year, or every season of every year. And for 1,000 megawatts of nameplate wind plant, you need to store 320 gigawatt hours in order to jump this ditch. The cost of cavern storage, if you had the geology available, if you had a continental hydrogen pipeline system, which we could begin to explore with a pilot plant, you find that the cost of the caverns and the cushion gas is only about 3% of the total capital cost of this $2.6 billion 1,000 megawatt nameplate wind system. And to provide that amount of storage with compressed air energy storage would cost about $13 billion. VRB flow batteries would cost about $160 billion, and the same amount of storage with caverns is about 25 to 50 million. The trouble with electricity transmission, the grid is nearly full, so the new renewables are going to have to pay for transmission. Low capacity factor, if you've got a new electric line connected to a wind plant with a 40% capacity factor, so does that line or any segment of it that's attributed to the wind suffer that low capacity factor. Wide right-of-way compared to pipelines is necessary for electric lines, and that leads to the NIMBY problem. People just don't want these things in their backyards. They'll fight them for decades, and FERC does not have interstate jurisdiction over new electric transmission lines. They do over pipelines, but not over electric lines. And the gigawatt scale wind that we've seen in this country so far has really cherry-picked the best wind sites where there's very low-cost access to transmission. If we've been depending on the production tax credit, now 2 cents a kilowatt hour, and we've been unable to provide really any significant smoothing or storage. The grid instability leads to costs for the utility companies trying to integrate this amount of renewable source energy. Sorensen from Roskilde says we could supply all of Denmark's energy, not just electricity, all the energy from wind power if we converted about 15% to hydrogen and stored it in a couple of salt caverns extant in our country now. USA could do the same, and maybe we'd want to start with transportation fuel. California, for example, to fuel 20% of its small vehicles with hydrogen, 9 million of them, 20% of 45 million, if they got 78 miles per gallon on hydrogen, 150 kilograms of hydrogen per year, requires 1,800 million kilograms of hydrogen from renewable resources, we suppose, 1.65 million tons. That would require the full output of 23,000 megawatts of nameplate wind generation. That's the amount of wind installed in the whole country at this time, just to supply the hydrogen fuel for 20% of California's cars, plus for 92 storage caverns in order to firm that amount of energy. So you'd have to access the good salt geology. Sandy Thomas in 08-09 concluded that you cannot achieve the greenhouse gas reduction goal of 80% below 1990 levels without hydrogen-fueled fuel cell vehicles. We've tried everything else. Maybe it's time to build a pilot plant for Renewable-Source to hydrogen complete energy systems. And this is what it would look like. There are alternatives for the line pipe material. This is fiberglass over steel to try to eliminate the hydrogen embrittlement problem. This is polymer metal tubing, which would probably eliminate the hydrogen embrittlement problem because there's no steel in there at all. This can be continuously fabricated in the field up to 36-inch diameter. This should be explored as part of our pilot plant project, and we proposed that in our ARPA-E. The industrial gas companies have very successfully and safely operated hydrogen pipelines throughout the world, but they've done so making them out of low alloy steel, operating them at rather constant pressure and rather low pressure, only 30% of their specified minimum yield strength, whereas the natural gas people are at 80%, and over short distances. Now the wind people say we need this much new transmission to supply 20% of our electricity by 2030. Does it make any sense to try to access this good salt geology down here by building a hydrogen transmission line through that windy part of the country, accessing the wind in Canada, and then distributing it to the coasts? We don't know. We haven't done the study. We haven't built a pilot plant. That's why we need to start now to build a pilot plant to find out whether we can even do this modest amount of wind to hydrogen to fuel all of our small vehicles in this country. Still a tiny part of our energy economy, and of course that would have to be delivered 500 or 1,000 miles away by transmission line. So the pilot plant concept, International Renewable Hydrogen Transmission Demonstration Facility, complete hydrogen renewable energy systems, must be considered a corridor, could build it in Iowa, destination Ames. This is the process that you would go through. The same for ARPA-E, probably. It would get a little more complicated as you got into it. We'd be coming up with some other features of it. And we'd hope to achieve some of these outcomes. It's an extraordinary opportunity aside from ARPA-E. We should start the process now of building such a pilot plant for renewables hydrogen energy systems. Wellinghoff says we can run the world on renewables. We don't need any new coal and nuclear plants. Of course, he was criticized for that, but he's the chairman. I guess he can say what he wants. This is the opportunity now. If you'd like to join me, give me your card, and I'd be glad to talk about it. Thank you very much. I do have some handouts, some DVDs if you want to see me after the meeting. Thank you very much.
Thank you, Bill. We need more like Bill.